All right, it's 11:30 Arizona or Pacific time, and I don't know if it's morning or afternoon for you, but I appreciate you signing in and joining to this webinar. I hope everyone is staying safe and healthy out there. My name is Nathan Antono. I am a process and technology engineer with Archer Western, and I'm very excited to be facilitating this webinar for you today. We have three fantastic speakers lined up for you. This is going to be a topic of anaerobic membrane bioreactors, and we're going to be talking about the fundamentals, field experiences, and the future of this technology. So Andrew Gilmore is going to be leading us off from Carollo Engineers. He's going to be covering the the fundamentals of this technology. The second speaker is Mike Allison from Evoqua Water Technologies. He'll be covering field experiences, and then we'll be wrapping up today with Dr. Bruce Rickman, and he's going to be handling what the future may look like and some of the challenges that we need to overcome with this technology. So I hope you can all see my screen. I'm going to attempt to forward my slide here. Okay, so the agenda today, it's an hour and a half program. We're going to just do some simple introductions here quickly. I'm going to introduce each of the three speakers, and then we'll let Andrew kick it off. Andrew's going to talk for 20 minutes or so. We'll have a brief Q&A session after his topic, just time permitting. And then we'll at noon, we'll let Mike take over again for about 20 minutes or so with a few minutes of Q&A. And then finally, Dr. Bruce Rickman. And then at the end of it, we'll be allowing more Q&A at the end to wrap this up. So for Q&A, there's a question box to the right of your screen, so you can simply type in any questions that you may have along the way. I'll try to gather those up and ask those at the end of each section and at the end of the entire program. And I'll facilitate any questions, and if I don't get to them, I apologize, but I think we're going to have some pretty good topics here. And let me just get into the speakers. Actually, one other note, the PDHs and CEUs, those are going to be available. It's an hour and a half credit, so those will be emailed to each of the attendees, and this will be recorded. So Shayna Schwartz, who's kind of operating behind the scenes here, she is going to be recording the entire session here and then posting that onto the AZ Water Biosolids Committee webpage, as well as some social media posting as well. So with that, I'm going to get into the speakers. Andrew Gilmore is a vice president with Carollo Engineers. He has been there for 23 years. He is the MBR chief technologist and is also a part of the Carollo technical practice leadership team. So he has a lot of MBR experience, which is why he's a great addition to this lineup. He's designed over 24 MBR projects, some of them as large as 250 MGD. So some really big stuff out there that's coming along the way. And these are not going to be anaerobic systems, but he's going to talk about some of the similarities between traditional MBR and anaerobic MBR. He's got some hands-on experience with piloting during the early days of MBR development. And he's a graduate of SUNY at Stony Brook, as well as Cal Poly, where he got his master's. The second speaker today, Mike Allison, he's a process engineer with ADI Systems, which is an Evoqua water technology company. He's been there for 8 years, and he's a technical practice leader for that company. He's co-authored several papers and presented at WEFTEC. In terms of MBR experience, he's been involved in a lot of startups and troubleshooting of many anaerobic MBR systems, as well as a lot of hands-on experience with piloting as well. His education comes from New Brunswick University, where he achieved his master's degree. His thesis was treatment of acrylic acid production, wastewater using anaerobic MBR. And he's published his research at the Journal of Hazardous Waste, which was presented at WEFTEC and IWA Membrane Conference. And the final speaker, Dr. Bruce Rickman, He's a Regents Professor of Environmental Engineering and Director of the Biodesign Sweetie Center for Environmental Biotechnology at ASU. He's a member of the National Academy of Engineering, a Fellow of AAAS, WEF, IWA, AEESP, and NAI, and is a distinguished member of ASCE. He's done a ton of research, all of it really with a focus on managing microbial communities to provide services to society. Some of those services include generating renewable energy, cleaning water and soil, and improving human health. Some accomplishments Dr. Rickman has achieved is he's the first Clark Prize winner for Outstanding Achievement in Water Science and Technology from MWRI, the Walter Hub Huber Research Prize, and the Simon Fries Award from ASCE, the GM Fair Award from AAEES, and the Perry L. McCarty AEESP Founders Award. He is, I think, very recently the co-winner of the 2018 Stockholm Water Prize, which is a pretty significant deal. He's published over 720 journal articles, books, book chapters, and has 16 patents. Along with Dr. Perry McCarty, Dr. Rickman co-authored the textbook Environmental Biotechnology Principles and Applications, and I proudly have a copy of that on my shelf and definitely have referenced that throughout my career. So a great honor to have him here as well. So with that, I'm gonna have Shayna switch it over to the first speaker, Andrew Gilmore.
You're gonna give me control, right, Nate? There we go, show my screen. Let's see. There we go. See my screen okay, Nate?
I can see it, yep.
Yeah, smooth slide. Great, thank you. All right, well, thank you for having me. Pleasure to be here to chat to you all about anaerobic MBR bioreactors. This is a topic obviously interesting to me as someone who's been working on MBR projects since 2001, and of course over the last several years, especially a lot of industrial clients have asked about anaerobic MBRs, and we've evaluated them at a pretty high level scale. In addition, I've done some work with a couple of universities looking at doing more lab style stuff on anaerobic MBR. So it's great to get this pulled together between myself. The idea here is I'm just going to prep everybody really for those discussions that are coming next. Some of the basics, of course. So I'm going to talk through a little introduction on this technology, different configurations that are out there of how you can put together an anaerobic MBR, applications, where does this fit into our industry, some of the facilities that are out there as far as what has been done at a lab pilot scale as well as full-scale facilities, and that's going to dovetail pretty well into the next presentations that are coming up as well. And then discuss some of the challenges that we're seeing with this technology as far as the application, some of the early work that's been done. So of course, one of the technologies we're talking about here is anaerobic treatment. Oh, Microsoft PowerPoint just stopped. Okay, give me a moment here. Apologize. Crashed. Is that back up again, Nate? Do you see it, or have to reshare?
No, I can see it, Andrew. Yep.
Okay, sorry about that. I don't know why that happened. Okay. So one of the technologies we're talking about here is anaerobic treatment. And given this is a biosolids group, I'm sure you're all familiar with anaerobic treatment. The process is absence of air, a four-step biochemical process. Usually you see this at municipal plants and industrial plants too. Typically, though, at larger facilities because of the scale and need for the solids to make this technology viable. There's been a lot of good studies done over the years that depending on where you're at in the world, location-wise, for power and whatnot, and temperature, what makes sense for putting in anaerobic digestion. I've seen numbers anywhere from 4 to 10 MGD as a bottom level for anaerobic digestion. That's where it gets interesting when you start coupling with MBR treatment, especially when you're looking at building it from small up to large to prove out the concept, right? Now, anaerobic treatment is not common, though, in the liquid stream. You typically see it in, like I said, for the solids treatment, right? So now we're talking about, for anaerobic MBR, bringing it into the liquids mainstream. So again, it's a little bit of a different configuration we might be used to on the municipal side, at least. I'm not going to belabor this. I'm sure all of you have seen a million presentations over the last 20 years about what is an MBR. But the basics here is, instead of a conventional plant where you have clarifiers and filters, you put in a barrier membrane separation process, which becomes the best clarifier in the world, so to speak. And then you can run your aeration basin up at a higher mixed liquor and get a higher level quality effluent. Do less and more space, kind of following along with the intensification concepts that are being talked about more and more these days as we have challenges with existing footprint and then making plants that are already in existing footprints do more relative to nutrients or even potable reuse. And now we talk about anaerobic MBR and take those two concepts and mash them together, so to speak. You then have this anaerobic bioreactor followed by your membrane. And I'll get into a couple different ways, that this can be configured. This is, a generic flow diagram. And then, of course, you're going to get some biogas off of the anaerobic bioreactor, which we'll talk about as the main driver here. So why is it interest? Why have we been talking about this? Why are people trying to do this? Well, it's to reduce energy usage, right? So anytime you do anaerobic treatment, you're doing void of air, so you get rid of your blowers, diffusers, all that energy hog that you usually have in a liquid stream, and instead you let the biology do the work for you and generate gas, right? So potential power. And as well as, coupling with water reuse. Once you get the membrane in there, you do have that either 0.2 or 0.04 micron barrier, depending on what you're using, which then right in and of itself is going to give you a good water quality. And then, overall sustainability. That's something that, depending where you are, again, sustainability is something that's very much of interest these days as we plan out these facilities now and into the future. So this technology has a lot of promise for that, of, taking these things to energy neutral or energy positive. This is just a brief history of some of the things that have been looked at in the past on anaerobic MBR. Really early on, the 60s, some people try to take a UF filter and put it in the back of a septic tank. So in some ways, you can call that a anaerobic MBR, trying to see how that would work together. And then also looking at piloting. In South Africa, there's a pretty early pilot in the 80s where they put in a configuration and documented that. And then Japan went through a pretty extensive research program in the 90s to try and further this technology. And then I got some information later on, lab scale stuff that's been done in the US and in Europe as well. And then we're going to hear, of course, from the two later presenters on concepts as well. So as far as the configurations go, generally you have some that are very similar to MBRs that you might be used to seeing, where you there's also the option of doing like a side stream or external type option, and then the immersed or submerged type. So first, external membranes. This is where you see it sometimes in the lab type scale work, where you've got the bioreactor as a tank, and then you're pumping to whether it's tubular membrane or ceramic membrane. I mean, it can be the same. That's external, and you're returning back that flow back into the tank. Makes it pretty easy for lab style tests or even pilot scale testing, because the modular nature keeps those membranes out of the anaerobic bioreactor, so you can kind of control these things separately. The other is submerging it right in the bioreactor. where you put the membranes right into it. And this of course, was what we saw a lot in the early days of MBR, of putting a lot of the, especially hollow fiber membranes in the early days, were put right into the bioreactor to see how that would work out and how that would help the footprint. Over time, the industry started taking those hollow fiber membranes, at least, and put them in separate tanks. Of course, flat plate. There's a lot of flat plate projects out there that do put the membranes right into the bioreactor. But regardless, this is another way you configure it. And then, of course, in any of these things, you have to scour the membranes. And one of the ways to do that is with a gas barging system. So instead of using air scour, you have PD blowers or turbo blowers, or kind of flavor of blower the owner prefers or is suitable to scale, would be eliminated in the situation. Use that gas that you produce to scour those membranes. Again, trying to reduce the energy consumption. And then this is more, I'd say, more typical to what you see, at least in a hollow fiber world on the MBR side, where you've got an anaerobic bioreactor tank where you're doing that process, followed by a tank where the membrane is submerged in that tank. And then you can have, in this situation, you got a lot better control, arguably, over the process and what's going on in each tank, as well as the ability to clean inside of the tank and whatnot. Typically, you see this in much larger facilities, as opposed to the external tubular style, which is more, at least in my opinion, possibly more of like a lab type scale, whereas this you could see in a pilot or even full scale type approach. This is a diagram of an approach that Dr. Rickman is going to talk through, that he and his Perry McCarty, his partner Dr. McCarty, have been working on, where they're separating the multi-stages. They got a first stage followed by a second stage, and they call them a fluidized MBR. And of course, I'm going to let him talk more about that, but at least to prime everybody that this is another thing that's being tested, looks very promising. He's going to spend a lot more time talking about than I will on what he's seeing in the results and how it solves some of the problems that I'll talk about, or challenges with this type of anaerobic MBR. And then the process that Mike Allison is going to talk about from Evoqua is this ADI anaerobic MBR, where they have some pre-treatment, which of course, those that are familiar with MBR, any MBR should have some sort of pre-treatment, especially on the screening side. Typically a perforated plate screen, 2 millimeter, 3 millimeter, depending on what the supplier requires, to protect those membranes from materials that can cause abrasion or clogging of the membranes. Followed by the equalization tank, which in any pilot or full-scale equalization is a good thing. As you probably know, membranes have as a permanent barrier, there is a limit to how much flow range they can handle. So equalization helps dampen that peak that can be handled through the membranes. Then they have a continuously stirred tank reactor, which is the anaerobic part. They take the biogas off to a power generating facility or a boiler, whatever it may be. Again, this is part of the benefit of trying to get towards either energy neutral or energy positive, is taking this biogas. And then their process are followed by an external membrane tank where they recycle back into the anaerobic zone. And then the sludge goes off to a dehydration equipment. And then the rest of the flow, the permeate or filtrate, if you will, goes on to additional processes, which again, Mike will get into that. But again, prime everybody of some of the things you're going to be seeing later in this webinar. So as far as applications go, obviously the first one that jumps out is industrial, and this is where for a mainstream liquid stream treatment process, anything that's anaerobic, if you're familiar with upflow, anaerobic sludge blankets, that kind of technology, they like the high strength organic loading, right? It's a lot of good fuel for the process. So you look at like food processing facilities, pulp and paper, textile, and pharmaceuticals. So those are some of the things, especially when you look at the list of facilities that pilot tested this, lab tested it, And then, of course, when Avoca starts talking about what they've done, similar, food processing, whatnot, is where it makes a lot of sense. And I've seen some of these tested and been applied on food waste as well, pure food waste, as in excess food waste from whatever it may be, whether it's multiple grocery stores or a food processor itself. And of course, that leads into kind of a municipal concept, is where you can see as being kind of a challenge is municipal wastewater, especially relative to industrial wastewater that could be, a BOD of 5,000 or 10,000. We're lucky to see 250 or 350 on a municipal side, which can create a challenge to make this process viable. But it is, of course, one of the challenges that, we all in the industry are willing to take and try out, especially because they're attractive for sustainability potential, right? So for the ratepayers, what better story is there than the investment they're putting in is generating back power and energy, whatnot, and reducing footprint from a sustainability standpoint. Relative to facilities and operations, not a very big list of facilities and operations as far as I'm aware, but there have been a lot of pilot tests and pilot scale. So I picked out a few select ones just to kind of highlight again that, we're talking about very much the industrial side, food side. So you got, whey and cheese, and what they've tried doing there was a two-phase system with an external membrane. So two-phase digestion, really anaerobic digestion on the liquid stream, followed by an external membrane. And the membrane they use was ceramic, which is definitely of interest and pretty smart, because ceramic is a pretty robust membrane. It can be higher cost, but makes a lot of sense for this kind of application, especially when you're going to try and test it out and you're worried about how well it's going to work and getting good data. On this, the COD feed was pretty high, 68,500, but they were seeing good COD removal, 98.5%, which is great. This facility here is pretty small as a pilot, looking at about, I think the reactor is somewhere in the order of like 15 liters. So pretty small, pilot lab scale application. On the brewery side, they did a reactor with external membranes. Similar, they used ceramic membranes. The feed wasn't quite as concentrated as the whey facility, but likewise, they're getting good COD removal. This was also pretty small, about under 5 liter reactor tank. So again, very small lab scale. Pulp and paper, they did submerge, where they put the membrane into the reactor tank. They used a PVDF membrane, so ultrafiltration, hollow fiber type. The feed this is getting a lot lower down the 2,000 to 3,000 range, and they saw some variable COD removal, still promising. This one's around 10 liter lab scale. Another example is slaughterhouse, which those that have been to slaughterhouses or seen some of the big meat packing places that are unfortunately in the news a lot today, they tend to use a lot of anaerobic digestion because of the high strength that they get. You can see here it's up around 10,000 for the COD. Similar, they had external, tank with external membranes. They use an UF membrane, and they were seeing good removal. This is a little bit larger, 50 liters, still pretty small. And then the last one is actually a pilot where they use that upflow anaerobic sludge blanket with external PVDF hollow fiber membranes. They're getting 87 to 94% removal, and it was more of a pilot scale, so a little bit larger, outside the lab type system. Excuse me. On full scale, and I think this is something that Avoca will have a lot more information out here, more updated, but regardless, here's some stuff that I've been able to gather, which is, a wheat and starch facility where they've got UF membrane. There wasn't any information on their COD feed, but they reported COD removal, 78%, which isn't phenomenal. but still getting good removal. Maize processing, tubular UF membrane, they had 15,000 coming in, they were able to reduce it 97%. Salad dressing, this is, I believe, the one that Avoca is going to talk about today, where they had an anaerobic reactor followed by an anaerobic MBR, use a flat sheet membrane. COD feed is up around 34,000, and they're getting fantastic removal. And then alcohol stillage, where they've got an anaerobic MBR followed by anaerobic MBR submerged. This is one I want to do more research on myself, kind of see how they have this one set up in a multiple stage the way they do. And then the last section here we're going to talk about briefly here before we go on to the next, folks, is challenges. So some of the challenges we see right now is, lack of full-scale systems. So, the data set, the information on how these things operate, there's not much information out there. Of course, if a client or if you are an owner or whatever it may be, and you're interested in this, it gets more challenging to go and see examples and then figure out how to use those examples for your own situation. One of the things that Dr. Rickman is going to talk about is the potential for methane to get into the permeate, and then, well, what does that do to the system after the anaerobic MBR? There's also very limited studies on the fouling, looking at EPS and SMP relative to how that impacts the fouling and how that's produced in the anaerobic process, and depending on how the SRT or even the feed to the anaerobic process, what is that going to do to those different features that impact fouling? Filterability too is something that personally I've not seen much data on yet, as far as how well anaerobic treatment is filterable by the membrane. And then the biogas sparging, that is a usage of the gas that you're trying to produce. So depending on the type of membranes, what kind of fouling you might have, and the flux rate you're running at, is how much of biogas do you really need to use, and then how much of that are you cannibalizing from what you're trying to use to produce power, energy, and money. And then lastly, pilot testing, there doesn't seem to be enough of it out there, but of course, the pilot testing is going to be very plant specific and area specific, because each waste stream is different, especially on the industrial side. This is something where pilot testing is something that would be highly encouraged, kind of like we were about 20 years ago on the MBR side. Kind of almost need to go back to those kind of concepts to then see how it's going to work out for full scale and understand better about the kinetics. As far as operator familiarity, right? So especially for these small industrial plants, it's one thing to put in a treatment plant for them, and it's another thing to put in a high rate, high technology treatment plant. How familiar are they going to be, and do they have the tools to run that kind of facility? Similar, who's their support group? On the MBR side, conventional activated sludge side, whatever it may be, you can find several folks, in Arizona or any state that have these kind of facilities. But now when you start to get into something that has less user set, who is the support group then for these operators? And that's something to consider. And of course, the odor potential. Anytime you got anaerobic treatment, you have potential for odors that you have to capture and treat, and that can become a nuisance depending on where you are. And then the other unknown in this, because there isn't many full-scale facilities in time, whatnot, is what does this mean for membrane lifespan for the membranes, compared to typical MBR type situations. So I think with that, I am at my allotted time. Oh, I'm a minute over. Sorry, Nate.
No, I'll ask. I didn't see any questions come through, so I'll just throw one at you, and then we'll move on to Mike Allison.
Sure.
But do you have a feel, Andrew, for maybe capital and operating life cycle cost? Do you have a kind of a sense of either of those items?
Yeah, and I think on the capital, that's an interesting question. I don't really know if I've seen much information on that, but it would be both that and the life cycle cost. I really see this being area specific, right? Because you're dealing with biogas generation off of whatever your feedstock is. The question becomes, what is that feedstock? What is that you're taking in? How much how much fuel is there, fuel potential is there, how much do you need to use for cleaning the membranes and the sparging, and then of course in that region, what is the power cost, what kind of incentives are there? Do you have a power company that is open to doing power purchase agreements? All that we need to fold in and see if it's even economically viable from a life cycle cost standpoint. But I think that's again one of those things that we need to start seeing more of these facilities piloted and built. And of course, I'd be interested too, like when I hear the VOCA presentation from Mike, what they're seeing, if they're able to share, and if they've been able to figure out any real trends on costs, or if it's just really hard to figure out because it's so location and client specific.
Okay, good enough. Thank you.
My pleasure.
Shayna, could you switch over to Mike Allison, please?
Hey, Nate, can you see my screen there?
Yes, I can see your screen.
Okay, perfect. Okay, I'll get going here. So I'm gonna kind of pick up where Andrew left off. So I'm gonna talk about some of the lessons we've learned in applying anaerobic technology. So kind of what I'm gonna go through, I'm gonna start going through the basics of anaerobic MBR. So this will be a little bit of repetition from what Andrew went through. This will be more geared to the anaerobic MBR systems that I'll be talking about after. So then I'm going to go through some of our installations, talk about briefly, why they chose anaerobic MBR, why it works for them. And I'm going to share operating data on one of the sites just because it gets pretty repetitious if I did for all of them. And then I'm going to talk about some of the lessons we've learned, in building all these sites. We've obviously learned, learned some things along the way. And then kind of tee it up for Dr. Rickman at the end, talk about what's next for the anaerobic MBR. So just a little bit about ADI systems. So we've been around for about 35, 40 years. We do a lot of industrial wastewater projects. We have over 300 full-scale biological installations, mostly for food and beverage customers. We typically do design build projects in the US and Canada. So a little bit about the anaerobic MBR. So as Andrew kind of showed in his presentation there, the anaerobic MBR is a process that incorporates anaerobic digestion and membrane filtration all in one process. The anaerobic MBR is well suited for treating food processing wastewaters, which contain high concentrations of biodegradable organics, suspended solids, and some fat, oil, and grease. So the installations I'm going to be talking about will all be from an industrial background. So we won't touch on any municipal work. So as Andrew kind of pointed out in his presentation there, you can see this is a typical graphic of anaerobic MBR with submerged membranes, which is the type I'll be talking about. So raw wastewater goes through pretreatment equipment, which typically will consist of screening or grinding before it's fed to an equalization tank. From there, it goes to the anaerobic CSTR. So that's a complete mixed tank. From there, the sludge is recycled between the CSTR and the membrane tank. Now, the reason we have that big recycle loop is that as we're pulling out the clean water, we leave all the solids behind. So we need to recycle those solids back to the CSTR so that they don't build up in the membrane tank, thus making it hard to pull through the membranes and increases the fouling rate. The clean permeate, which is withdrawn through the membranes, is either sent on for final treatment or sent to city for final treatment before it's finally discharged. So some of the benefits of the anaerobic MBR is that it combines anaerobic digestion with membrane filtration all in one process. So we get some of the benefits of anaerobic digestion technology, which is very, very good for wastewaters with high concentrations of COD, BOD, TSS, and fat, oil, and grease. And some of the benefits of the CSTR is that we get a high substrate to biomass contact because the system is fully mixed, so we're getting very good contact between the sludge that's in there and the food waste that we're sending in. And then on the back end, the membrane gives us a physical barrier to provide absolute solids liquid separation, so we retain all the biomass in the system. So some of the other benefits of the anaerobic MBR is that the system will produce a high quality solids-free effluent. The biogas production is maximized and can be used as an energy source. And the and aerobic polishing may not be required in some cases. The photo on this slide shows a typical image of anaerobic MBR samples. You can see the raw wastewater sample with lots of suspended solids and organics on the left-hand side. In the center is the mixed liquor, so it's kind of typical black sludge. The concentration in this sample is around 25,000 milligrams per liter. And then you can see the final effluent on the right there with virtually no suspended solids. And so this site here, the COD of the raw wastewater is around 17,000 milligrams per liter, and the final effluent COD would be less than 30 milligrams per liter on average. So a few other benefits of the anaerobic MBR is that they can very compact footprint. They can fit in very small spaces when required. So the reason that the systems can be compact is because the membranes retain all the biomass in the system, and thus we retain a high inventory of active biomass is retained in the system, and there's no fear of losing biomass since the membranes provide that absolute barrier. This allows the solids retention time and hydraulic retention time to be operated completely independently, because the only way we waste sludge is when we choose to waste sludge, because the membranes will retain that biomass in the system for us. So operating at extended solids retention times will improve digestion, maximize biogas production, and minimize waste sludge production versus some conventional anaerobic technologies. A couple other benefits of the anaerobic MBR is that often wastewaters with high concentrations of TSS or fat, oil, and grease are good candidates for anaerobic MBR because these components can be challenging for conventional anaerobic treatment technologies. So one benefit of the anaerobic MBR is that these components don't need to be removed upstream of the anaerobic MBR. They can be fed directly to the anaerobic MBR with minimal upfront treatment. We don't need to necessarily remove them. So this really simplifies the overall process and can eliminate the need for some treatment steps altogether. Another benefit of the anaerobic MBR, similar to other anaerobic technologies, is that waste-activated sludge from downstream aerobic processes can be sent to the anaerobic MBR for digestion. Since the solids are retained in the system, we can maximize our WAS sludge digestion. And another benefit of the anaerobic MBR is a very robust process where we have the membranes. We're controlling how much sludge we maintain in the system. So therefore, we're setting our F/M ratios by retaining sludge in the system. And kind of in concert with that is that we don't rely on granular sludge. So we're not, some characteristics of wastewaters that would be challenging for granular sludge, we don't have to worry about that because we're retaining it with the membranes. Now, the anaerobic MBR systems that I'm going to talk about today are all going to be based on Kubota membranes. So I know Andrew discussed there were different types of membranes. So there's the tubular one and flat sheet would be two common ones that people have worked with. So Kubota manufactures the flat sheet style of membranes. So you can see in the photo the membrane cartridges are housed in cassettes, and the permeate is drawn through the membranes, leaving the solids behind in the tank to be recirculated back to the CSTR. In order to ensure solids don't build up on a membrane surface, the surface of the membranes needs to be cleaned. For Kubota membranes, the way this is done is by scouring the membranes with biogas. Biogas is discharged below the membranes using coarse bubble diffusers, and the biogas passes upward across the membrane surface, thereby controlling the buildup of biomass on the sludge surface. The other way that the membranes are kept clean is by chemically cleaning them. Now, for Kubota membranes, we're typically only cleaning the membranes every 3 to 4 months on average, and we're just soaking the membranes in cleaning chemical and letting it soak through. So the membranes are only offline for a few hours while this is done. So now I'm going to kind of switch gears and start talking about. I'm going to go through some of the systems that we have and talk about how they work, why the anaerobic MBR is there, and how it works. So the first system I'm going to talk about are the anaerobic MBRs installed for Ken's Foods. So Ken's is the leading producer of barbecue sauce and salad dressings, and the wastewater from these plants contains high concentrations of COD, TSS, and fat, oil, and grease. which makes them a good candidate for treatment with anaerobic MBR. So the first plant I'm going to talk about, we have 3 anaerobic MBRs at Ken's plants. The first one is in Marlborough, Massachusetts. So the plant in Marlborough was being expanded and production was increasing by 60%. Therefore, the wastewater treatment system needed to be upgraded as well. So after completing a successful pilot study on site with ADI, Ken's installed the first anaerobic MBR in North America, and the plant was commissioned in 2008. Installing the anaerobic MBR allowed the plant to be upgraded within the limited footprint available, because existing infrastructure was reused on site, and that is what allowed the flow through the plant to be increased without increasing the structures on site. So the only thing that was really added for the anaerobic MBR was these 4 membrane tanks, because we used the existing anaerobic digester that was on site. And you can see the 4 membrane tanks. You can see the roofs on the top of them there. And then on the other side is an SBR. It's converted to a one-stir aeration tank, which polishes the effluent from the MBR before it's discharged to the city. Here's some operating data from Ken. So this is, you can see the influent COD. It ranges 35 to 40,000 milligrams per liter in the influent, and then you can see the effluent typically averaging under 300 milligrams per liter. So we're getting, near complete removal of all the organics that are being sent to the system. So this is typically what we see of all the anaerobic MBRs that are treating food processing wastewater. We'll see, high influent CODs, and then we'll see very low effluent CODs. So I'm only going to look at data for this first plant, but all the other ones we'd see similar results, just different numbers. So the next slide here, this is on the total suspended solids in the system. So you can see Ken's wastewater, just by its nature, has very high concentrations of suspended solids. All consistently over 15,000 milligrams per liter. Now, since the membranes provide complete retention, the effluent off the system is very, very low. And so the membranes obviously do a great job at retaining that biomass, meaning that we have no solids that are coming through. So in the 12 years the system's been in operation, there's been no membranes replaced from the system. So the membranes are holding up very well under the conditions here that we have at Ken's. So Ken's second anaerobic MBR was installed in Georgia. So this plant treats 200,000 gallons a day of barbecue sauce and salad dressing wastewater. So Ken's decided to install the second anaerobic MBR after the success of the Massachusetts installation. And the existing aerobic system that they had there had aging infrastructure, and the system was struggling to meet the effluent discharge limits. So the system was in need of an upgrade. Therefore the anaerobic MBR was installed.
Hey, Mike.
Yep.
I'm just going to interrupt you for 1 second.
Yep.
The audio is going in and out a little bit. Could you just make sure you just stay close to your speaker?
Yep. Okay, will do.
Thank you. Sorry about that.
Okay, so the third system I'm going to talk about is for Ken's Lebanon in Indiana. So this system was built in 2009 when Ken's installed a new facility in Lebanon. So the way, once again, wastewater from barbecue sauce and salad dressing. So you can see here, the wastewater is a great candidate for anaerobic MBR. We've had great success with these 3 plants. So all three of them work very well, and just the nature of the wastewater makes them very suitable for anaerobic MBRs. So the next, so these are 2 plants with plant A and B, we'll call them. So these are for supermarket food waste. So we've installed 2 anaerobic MBRs that treat supermarket food waste. So when food from grocery stores can't be sold or donated, it gets returned to distribution centers, and then they have to deal with it. So for these 2 particular systems with anaerobic MBRs, what they do is when the food is returned to the distribution center, it's separated, they remove the plastic, everything else, and then it's macerated and liquefied into a form that can be fed to the anaerobic MBR. So since the anaerobic MBR provides complete retention of solids, the solids from the food waste are fully digested. So the influent from these systems have very high concentrations of COD and TSS. So the COD is over 125,000 milligrams per liter, and the TSS is over 70,000 milligrams per liter, so 7% solids. And the effluent quality coming off the anaerobic MBR is great. The COD is less than 2,000, and the TSS is negligible, very low coming off these systems. So you can see, regardless of the system, we're going to get that great effluent quality that comes off the anaerobic MBRs. Next system I'll discuss briefly is New Belgium Brewery. So New Belgium Brewery is one of North America's largest craft brewers, and they pride themselves on producing high quality beer under environmentally and socially responsible policies. That's kind of the company goal. So brewery wastewater typically consists of high concentrations of soluble COD and low concentrations of suspended solids. This composition makes brewery wastewater an ideal candidate for high-rate anaerobic pretreatment systems using granular biomass. Historically, high-rate upflow anaerobic sludge bed reactors or ultra-high-rate expanding bed granular biomass reactors have been the conventional choices for anaerobic pretreatment of brewery wastewater. These reactor configurations minimize space required for wastewater treatment. However, these high-rate anaerobic reactors are susceptible to process upset conditions due to changes in wastewater, spikes in organic loading rate, transient toxic inhibitory substances. So these process upsets can result in granule degradation, which is difficult for these systems to manage, decreased biological performance, and washout. So when MBB saw technology that would also, in addition to the brewery wastewater, would also digest hops and yeast to increase their biogas production, also as a waste diversion for the site. So this aligned well with New Belgium's environmental sustainability policies. So New Belgium didn't just want to meet the discharge limits; they wanted to fully adhere to their core values. So they decided that they wanted to continuously generate a very high quality effluent. So some of the challenges for New Belgium was that the brewery was expanding and the municipality surcharge costs were increasing. So that's why New Belgium was originally looking at doing something. So there's limited space on the site. You can see in the photo here, it's kind of in the corner of the site next to a road and a walkway. So there's very limited space, and also they did not want to disrupt the sounding area, albeit with emissions of light, odor, or noise. And they also want a system that would consistently meet their discharge limits. So after taking all these challenges into consideration, New Belgium determined that the anaerobic MBR technology would best meet their requirements. So with the increased load from the waste, hops, and yeast, the anaerobic MBR process is achieving greater than 99% COD destruction in a single process, in a single step. So this is doing that, kind of what New Belgium was looking for, producing a high quality effluent going direct to the city, and kind of gets rid of a lot of their concerns. The next system I'm going to talk about is Kelloggs. So Kelloggs plant in Pikeville, Kentucky, they were upgrading their plant and they needed to meet stricter discharge limits because the treated effluent was going to be directly discharged in a nearby river. So obviously previously they were going to the city, so they needed more treatment than what they had. So this wastewater plant was designed for a flow of 25,000 gallons per day, 5,000 of which was sanitary flow, which was going straight to the aerobic MBR. So the anaerobic MBR pre-treats the wastewater to remove the majority of the organics from the wastewater, and then the downstream aerobic MBR polishes the effluent to meet the final effluent discharge limits. So the anaerobic MBR provides, very good anaerobic digestion. It removes the majority of the organics, reduces the sludge production of the downstream aerobic MBR. So the average effluent concentration coming off the anaerobic MBR is 150 milligrams per liter with negligible TSS. So really, the aerobic MBR is just polishing that to meet your final discharge limits on nitrogen for the site here. So this shows how the anaerobic MBR and MBR can be used together to produce a very high quality effluent for final discharge. The final system I'm going to talk about is Buenos Candies. So this is anaerobic MBR in South Central Pennsylvania. So the anaerobic MBR here was installed because the plant was expanding. They're putting in a new line, and they also had stricter discharge limits coming into effect. The county changed their limits. They also had issues because they had an aging system with open clarifier, so there were odor concerns, and sludge settleability was the bottleneck for the system. So the Anaerobic MBR here was designed where we retrofitted an existing hybrid system. So the hybrid, the media was removed from the hybrid reactor, and mixers were installed to convert the hybrid into a CSTR. And then we used the CSTR coupled with an anaerobic MBR tank pictured in the slide here. And that became the anaerobic MBR. So the effluent coming off the system, and this is the picture that I showed earlier there, the influent, mixed liquor and effluent. So the effluent off the system, BOD less than 30, 5 milligrams per liter TSS. So the system, the organic removals changed or increased from previously they were getting about 60% COD BOD removal to now we're getting 97% COD removal. So they have no worries about not meeting their discharge limits like they did before. And since the clarifier is not being used anymore, they don't have any concerns with odors. So now I'm going to talk about some of the lessons we've learned through these systems. So the first one I'm going to talk about is the importance of pilot. So for many of the projects that I discussed there earlier today, pilots were completed before we started them. So since an anaerobic MBR is a newer technology, we don't have experience with treating all kinds of different types of wastewater. So you don't know what things we're going to run into or complications. So often we've done pilot studies on a lot of these full-scale systems to make sure the membranes are going to work. So things that we learn in pilots, we make sure that the wastewater is amenable to anaerobic treatment. It allows us to characterize the wastewater and see the impacts and changes from the raw wastewater on a small pilot system. The effluent results from the pilot can be used to size downstream polishing steps if needed. The photo here shows a pilot study that was completed last year. This pilot was operated for about 8 months, and throughout the study, many things were learned. But typically, one thing we're looking to learn during pilot studies, we're looking to study the fouling on the membranes or the compatibility of the raw wastewater with the anaerobic process. So the way that membrane failure rate is typically tested is by operating a pilot treating the same wastewater the full-scale system will be treated. Since membrane fouling takes time to be observed, many of the pilots operate for many months to ensure that membranes can stand up to the raw wastewater and can be effectively cleaned once they have fouled over extended periods of time. The constituents of the raw wastewater determine whether a given wastewater can be treated anaerobically with an anaerobic MBR or not. And not all wastewaters will operate at the same flux rate with the same membranes. Sometimes during pilots, you determine that the anaerobic MBR is not the best solution to treat these wastewaters, but we certainly are always learning a lot when we're doing pilots. Another lesson we've learned with the systems that I discussed there is the importance of screening. So screening is important because all anaerobic MBRs have potential to flood in different locations, whether it's in between the membranes for flat sheet or if it's in the fiber bundle for the whole fiber membranes. There's also potential to plug diffusers and pumps if the wastewater is poorly screened. So now, one difference with the anaerobic MBR, unlike most wastewater treatment technologies, is that we may not simply want to remove large particles, as these represent potential biogas for the system. So we may want these solids to be fed to the system. We just need to make sure they're broken down to an acceptable size before we feed them to the system. So either way, having well-screened wastewater makes the system a lot easier to operate. Kind of in concert with the screening is the importance of mixing, because mixing is what provides the contact between the substrate and the biomass. So we need to make sure that the CSTR is completely mixed so we get that good contact, so that we get those good removals that we were talking about. So some potential problems that will arise from poor inadequate mixing are floating scum, sludge, and then that poor sludge wastewater contact, which could create an unstable biological process. So some of the keys to ensuring good mixing are, optimizing the locations of the mixers that are installed, characterizing the wastewater properly, and see how it relates to mixing requirements, and ensuring sufficient mixing power is installed. Next lesson we've learned, which is with respect to redundancy. So just like any other wastewater system. The need for installed redundancy is important to allow the system to stay online and give the operators flexibility in operating the system. For anaerobic MBRs, this means ensuring the membranes are always able to pull permeate. So in order to do this, we make sure that several key pieces of equipment, such as pumps and blowers, we have installed spares. Also, often we'll have instrumentation that's installed where we have installed backups so that we can easily use another instrument if one of them fails. The final lesson here is just discussing some of the continual improvements. So we're constantly changing or upgrading the way the systems that we're doing here. You know, we get feedback from operators, installers, you know, process engineers that work with these systems day in and day out. And so we've you know changed things to make things easier for maintenance access, for troubleshooting. You know, we've changed materials to make things easier to put together. So these systems are you know evolving. You know, I talked about there are half dozen systems here, but they're you know it's a newer technology and it's continually improving. So that's something you know kind of to look forward to. So now I think you got a couple minutes for questions, and then kind of tee it up for Dr. Rickman to finish it off.
Thank you, Mike. We are about out of time. I'll give you one question, and then we'll flip it over to Dr. Rickman. So you mentioned post-treatment of anaerobic MBRs and one example of an aerobic MBR. Can you talk about maybe, is that a trend that you see, you know, going to be moving forward, that you see increasing with frequency, or is that more of a unique one-off kind of situation?
I don't know if it's necessarily a one-off, because it is, you know, they do kind of pair well together, because if you have a high-strength wastewater, then you remove all the organics from it, and, you know, all you're left with is, you know, just a low concentration wastewater. It does make sense that you just polish that wastewater off, get a DO up, get the nitrogen out, and then discharge it. So like the application I talked about at Kellogg's, like it was kind of a perfect application, because we had the COD coming in was fairly high, and we had, you know, strict discharge on this because we were going direct to a nearby creek. So the two of them together made, you know, work very well together in that instance. And that might be something that we see more going forward too.
Yeah. Okay. Great. Well, thank you. Okay, Dr. Rickman. Shanna, if you could switch over to Dr. Rickman, we'll get his section started here. And I can see your screen at this point. I just can't hear anything. So Dr. Rickman, I can see your screen, but I cannot hear you if you're talking.
Problem. I muted myself. Well, duh. I shouldn't do that. Okay, let's get going here. So my assignment here is to talk about the future. And so my title is Future Opportunities and Challenges for Anaerobic Membrane Bioreactors here. And let's see if I can make my slides move here. Goodness gracious. All right. All right, that's, oh, I see, okay. All right, good. All right, so first of all, I'm going to talk about the future, but to talk about the future, I want to talk briefly about the past. So in about 1985, I was asked to give a talk at a conference on anaerobic treatment of domestic wastewater. And I gave a talk and wrote a paper on it, and the theme was, you can't do it. It's impossible. And so, and on the screen here, I'm giving the 5 major bullets as to why I said, don't even try. It's never going to work. Well, years have passed, And now I'm singing a very different song. And so now I'm saying that we should be doing this and we can be doing this because things have changed. And so what I'm going to do today is talk about some of these roadblocks that I identified in 1985 and why they've been overcome and why the anaerobic MBRs are going to give us this opportunity. So I'm going to talk about the first three things today on this. So I'll talk first about opportunities. And it's going to be the anaerobic biofilm membrane bioreactor. And then I'm going to talk about two challenges so you can see beautiful blue opportunities and red challenges. Okay, here we go. So I'm going to begin with addressing these two really prominent roadblocks that I identified many years ago. The methanogens are really slow growing and you can't get a good effluent quality. Well, this is no longer a problem on it. And that's why is because we have now anaerobic membrane bioreactors, and more specifically, I'm going to talk about the anaerobic biofilm membrane bioreactors. And here's a simple schematic of what it looks like. And so the key thing is you've got a closed anaerobic reactor, and you can see off to the right, you've got the membrane. So we'll get, the usual membrane separations and the solids-free effluent. But what's key in here is you've got these biofilm carriers. They're shown by the little X circles with an X. And the goal of them, of course, is to retain biomass as the biofilm. And this creates several major advantages over and above the normal advantages of the anaerobic MBR. So what are those big benefits of the anaerobic biofilm MBR? Okay, number one, if you configure it correctly, the biofilm carriers are going to be a natural cleaning mechanism of the membranes. So they're going to be in there, they're going to be bumping against the membranes, you're going to get a gradual scouring of the biofilm off. So you're going to greatly reduce the transmembrane pressure loss. You're going to have to clean these membranes very infrequently, if at all. So this is a giant benefit, number one. Then giant benefit number two is that the biofilm carriers increase the biofilm accumulation. So the membrane is already doing this, but when you put the biofilm carriers in that, you then redouble the biomass accumulation benefit. So you can get really high ratios of SRT to HRT, and that translates into a smaller volume or a higher volumetric loading rate, and that translates into reduced capital costs. Plus, all this accumulation of the biofilm improves the already good process stability. And so you've got multiple benefits here, including in the process, the biofilm on the biofilm carriers. Now, I'm going to talk about one particular example, one that's been very well studied. We have some data on it. It's called the staged anaerobic fluidized MBR, or SAF MBR. And here's a schematic of it. You already saw this earlier from Andrew's talk. And so this is a two-stage system here. It was developed jointly by Professors McCarty and Jeho Bay. And they've been done really quite thorough testing of this in a number of countries around the world. And so what you have is on the left side, you have an anaerobic fluidized bed where the fluidized medium is granular activated carbon. And granular activated carbon is lightweight, it has lots of macropores, great for harboring these slow-growing methanogens and other organisms. It's ideal. So you have on the left side a regular fluidized bed, and you get most of the BOD conversion to methane there. And then the effluent from the first stage goes to the second stage, which also is a GAC-based fluidized bed, but you can see inside it, it has the membranes. And of course, they have to be inside the reactor because you're going to use the natural cleaning mechanism of the GAC bumping against the membranes to minimize the biofouling on this. So this has been tested extensively in Korea, Singapore, United States. And we've got a lot of data on it. Here is a picture of the demonstration pilot that was tested extensively in Bucheon, South Korea. Bucheon is near the airport in South Korea. And on the left side, it says AFBR. That is your fluidized bed. That's stage 1. And on the right side are 2 examples they tested of different membrane configurations for the second stage, where you have the membranes in there. So they tested this with real primary effluent, primary sedimentation effluent. So it's domestic wastewater after sedimentation. And here, of course, typical characteristics you'd expect for primary effluent, BOD and COD going in. Now, what's really important on this slide is to note the hydraulic retention times of the system. First stage, 2 hours. Second stage, well, they tried a few things, but none of them were very long, 2.6 to 4.8 hours, so that the total hydraulic retention time of the system was less than 7 hours. So this is not a big system. It's not taking up a lot of room, no big footprint on it. So they tested this again with the Rio wastewater over more than a year, almost 2 years of testing. And here are some of the results. I'm giving the BOD5 results here over almost 2 years of testing. So they went through summer, they went through winter, they went back through summer and winter. And so, you know, they got all the vicissitudes that occur when you are doing the real stuff. And here you can see that after a little startup period, they were getting effluent BODs less than 10 milligrams per liter, often less than 5 milligrams per liter. So this was really a huge, huge success. And again, they didn't have to clean the membranes. They didn't have the fouling problems. It was very reliable, very straightforward technology in this test in Korea. Now, you don't have to use granular activated carbon. You can use other media, and we can rely on the developments of biofilm media for the moving bed biofilm reactors, the MBBRs. Here I'm showing a schematic of an MBBR, and then to the right, an example of one of these MBBR carriers. You can see there's a lot of biomass inside these big pores of it. And then, you know, MBBR has been developed for aerobic treatment, so you can see at the bottom here we have the you know, activated sludge. It's being aerated, but it's full of these MBBR media. So that's the idea. So we can adapt these media for the anaerobic BF MBR because they have lots of biofilm surface area. They're lightweight. They're made for this kind of application. So our group is evaluating these kind of media right now. We happen to be working with Veolia, so I'm showing you some pictures of Veolia media that with them we're considering for these anaerobic biofilm MBRs here. And you can see, you know, in the bulk specific surface areas are pretty high. So this is you know, a really good thing. It's going to be very fine for accumulating a lot of biomass. So we're engaged in the testing program with Veolia on these. Okay, now I've been talking about the wonderful things about anaerobic biofilm MBRs, and now I'm going to turn to the challenges. And I'm going to start with what I consider the most important challenge, and that is all the methane that's dissolved in the effluent. And first of all, you don't want methane going out in your effluent. You want to be collecting it so you can generate energy out of it. So you can't afford to lose it financially. And second of all, it's a very potent greenhouse gas, and we don't want to be emitting it. And if it's not regulated now, it's going to be regulated, and you won't be allowed to do this down the road. So it's really, really important. So now let's look at the SAF MBR, where they actually assessed where the COD was going and where the methane was going. And so here in the next slide is a graphic of a typical output of where the COD went in the effluent from one of their SAF MBRs. And you can see here, there's about almost 60% of the COD went to methane. That's in the bottom and lower and left side. But you'll notice that in the SAF MBR study, there was more effluent dissolved methane than there was gas phase methane. Well, this is bad on both counts that I just told you about. So, we really can't do this. So our team, as part of our anaerobic MBR research, is developing a mechanistic model of what goes on in the MBRs. And here's one output from our model. This is a model in which we are assessing the generation of methane as a function of the influent readily biodegradable COD. And now the dashed line shows you what you would expect. The more COD you put in the influent, the more methane you get out. It's linear. It's kind of obvious. What's really interesting is the solid line curve that sort of runs up the left and the top. This is the fraction of the methane that should end up naturally just bubbling out and being in the headspace and collected. And what it's not there is in the effluent, leaving in the dissolved effluent or the permeate. And so I've put a couple interesting numbers to the right. So if you look at the graph, if you look at 5,000 milligrams per liter of COD going in, and to the right, it's at least 98% of the methane goes in the gas phase. And it's really easy to collect. It just bubbles out. That's good. If you go down to 500 milligrams per liter, it's about 0.5. But if you're down to, say, 200 milligrams per liter, like it might be in primary effluent, it's down here at about 25%. Now, this happens also to correspond to what they saw in the SAF MBR results. So we have some idea this is important. So you can see, particularly for low concentration influence, the problem of effluent methane is a serious one. And again, in any case, you don't want to lose the energy value, and this is particularly critical when you're on the lower end of the influent concentrations. But even if you're at the high end and you're getting 98 or 99% in the gas phase, you still don't want to lose that 1 or 2% to the effluent because it's such a potent greenhouse gas, and we just can't afford to let it go. So whether it's money we're interested in or global climate change, we have to capture all of the methane. All right, now the good news. The good news. There are devices available for extracting gases from liquid, and you can do it for methane removal from the effluent. 3M, for example, makes very fine units like this. They have been tested, and you can get 90+% recovery of the methane from the effluent with a very low energy cost. So it's out there, it's available. It has not been widely evaluated in these applications and needs to be. This is on our team's agenda for the next year or so, is to begin looking at the performance of these methane extraction units. All right, now I'm going to transition to the last challenge, carrier membrane compatibility. So let's start off with the good news. I've already told you this. Putting those biofilm carriers gives us great benefits. Membrane self-cleaning, more biomass retention, better SRT-HRT ratio, all those wonderful things. But, as they say, usually there's no absolutely free lunch. And so what experience has shown is that those carriers, even the granular activated carbon, can over time abrade the membranes and cause damage and reduce the membrane life. Now, this is something that Professor McCarty has identified as one of the main challenges for the SAF MBR, and they're working on it there. Our team is also beginning to work on this membrane carrier compatibility issue. Mainly we use hollow fibers like ultrafiltration membranes. Perhaps we can use ceramic membranes too, but one of our goals is to start evaluating systematically the impact of having these biofilm carriers in with these membranes and long-term effects of abrasion. This is something we'll be doing in the next year. We've identified the problem, we've got the carriers, but we haven't actually started this research yet, but it's on our agenda for the next year. All right, now I'm coming to near the home stretch here. So let me just review the take-home lessons on this. One, the anaerobic biofilm MBFR offers huge benefits in self-cleaning and better biomass retention, better process stability and performance. The SAF MBR has been extensively tested around the world. It works. It gives really low effluent COD, low TM transmembrane pressure drop. It's really, really good. And we can try other carriers. You know, we don't have to be wedded to granular activated carbon. In fact, our group is beginning to test other carriers in this application. But it's not all roses yet. And so we have challenges. Number one challenge is methane in the effluent. And this is everybody's challenge, not just the anaerobic biofilm MBRs, it's everybody's anaerobic MBRs, because we cannot be letting this methane go. We can't afford it economically, and we can't afford it from the point of view of global climate change. So we have to use it, but fortunately there is gas extraction technology that needs to be more evaluated, but it's, at least it's out there. And finally, there's this whole issue of abrasion of the membranes. You know, we got this beautiful membrane cleaning, but then it kind of beats up on the membranes. And we need to do a lot of work on this because we don't want to be changing out our membranes, you know, once a year. So, so that's another area that needs a lot of attention. So I'm almost to the end, but I'm going to give you just a short coda here. A few years ago, with some colleagues in China, I published a paper in Nature about what we called the resource factory. And it's basically capturing all the value out of wastewater, in this case of this domestic wastewater. And you can see the diagram here that after screening, you've got the two stages of the anaerobic MBR, generating methane. And then we also evaluated recovering the nitrogen and the phosphorus and producing really high quality water. So when we did this, the editors of Nature asked us to do an economic analysis of this, and we did so. So here is a summary of our economic analysis of operations. Does not include capital costs, but just operations. And so what you can see on the right side, you've got the operations costs for 100,000 cubic meters per day for a conventional activated sludge plant. You notice all of those bars are below zero. That means they're all big costs. And particularly that big black bar for electricity to run the plant, particularly to aerate the system. If you go then to the resource factory, as I showed you, you then really tremendously minimize all the costs, and you end up with a net positive energy output. Plus, if you can do it, you can capture the fertilizer and potable water value as well. And so you end up with a net positive. So we can turn wastewater treatment from a big cost center into a profit center for let's say the municipality on this. The situation is a lot better if you were to go to some high strength waste like some of the ones that Mike told us about. So with that, I have come to the end. I've told you my little story, and I'll be happy to answer any questions. And of course, we'll have our short panel Q&A at the end. So thanks a lot.
Okay, thank you so much, Dr. Rickman. That was fantastic. So we've got 10 minutes or so for some Q&A. I did see one question come through here. And I'm going to throw this out to Mike to start with, but I think any of the three speakers can certainly chime in as well. But the question is, do you all see a large accumulation of waste product or polymers? Additionally, with the biogas, what general compositions of gases are produced? And does extra treatment of the biogas need to occur? And then a final add-on, for the pilot studies, did you ever find surprising results that you wouldn't have expected with the anaerobic membrane efficacy? So, Mike, I'm gonna, the question is posted on the side panel. Mike, if you wanna.
Okay, I don't. I don't see it there. But I'll start with the biogas composition. So we're typically seeing, it's all dependent on the wastewater concentration, what's in the wastewater. But typically, we're seeing similar concentrations to what you'd see regardless of the anaerobic technology. So, we see anywhere between 60 to 70+% methane in the biogas. And in terms of the piloting question, some of the other speakers may have some stuff to share on this too, but we definitely we have done pilots where we have learned things. I can't say where. We have one where we started doing a pilot and the wastewater just started foaming, could not get it to stop foaming. So we never, it worked well, like treatability, it worked. But then when we went to pilot it, when we started scouring it, the system started foaming, couldn't stop.
Did that foaming occur in the bioreactor portion of it, or was this like a single system? Yeah. Okay.
Yeah, it's because you're putting the biogas for that scour, so that reacts differently than it would in a mixed system.
Yeah. And then in terms of, maybe I'll kind of take the first part of that question and just kind of throw it around here. But the excess sludge from the system, aerobic MBR systems, you have to obviously waste from these systems. I assume, maybe I shouldn't assume, but is that the same with anaerobic MBR systems? If you could tell me about the waste sludge and what typically is, how that's handled.
Yeah, so you still need to waste sludge from these systems, although, one of the benefits of anaerobic technology is that it produces significantly less sludge. So you'll only produce about 1/10 of the sludge that you would anaerobically. Just as the bacteria grow slower, so we don't produce as much sludge. And then that sludge can be, a lot of sites it's, put on land as fertilizer, as liquid fertilizer, or it's dewatered and taken off site for compost or something.
Okay, great. Dr. Rickman, I got a question for you. How does the anaerobic biofilm MBR compare to activated sludge in terms of size or footprint?
Okay.
Can it be retrofitted into an existing activated sludge facility?
I'm glad someone asked that question. So the first thing is that these systems are going to be much smaller. To treat the same amount of COD, you need a much smaller volume in an anaerobic MBR. What really limits the loading to an aerobic process is oxygen transfer, and eventually you just can't get the oxygen in. You have no such limit in an anaerobic process, and so you can load it up much higher, and so any anaerobic process, that's true. But then when you get the anaerobics with the membrane and the biofilm carriers in there, you can really accentuate that. So you'll have a much smaller footprint, which then gets to the second question is, well, can you retrofit? And the answer is yes, you could retrofit this. You'd have plenty of extra space if you say threw away, took out the activated sludge stuff and just put the anaerobic membrane bioreactors in the same spot. You wouldn't use nearly all of it.
Very good, thank you. Just going to search and see if there's any other questions posted here. I don't see anything yet. Oh. Okay, actually I do have a question here. Okay. So when functioning as a plant, how long do the membranes tend to last before they need to be replaced versus just cleaned? I guess, Mike, maybe that's a good one for you with your, all your installation experience that you have. How long do these membranes last?
So, we're still kind of learning that, with different wastewaters, but for most of the systems, we haven't had to replace them due to, the membrane deteriorating over time. Like sometimes there's been a physical, issue, but that's different. But like the Ken's Marlboro, which was our first installation, we haven't replaced the membranes there, and that's been 12 years here in June.
Oh, wow. And I guess Andrew or Dr. Rickman, based on your piloting and other experience, do you have any other thing to add to that, the expected membrane life, especially with the media, with the biofilm system?
Well, I mean, I'll just, reiterate. I mean, it is an issue with the biofilm carriers in there. It would, in some of the SAF MBR pilots, they did see some problems with deterioration, of the membranes, and so that's why I bring it up, is because they actually saw it. So that's why it's become an issue. I think it can be overcome, but yeah, it is still something that's on the table to be evaluated more.
Yeah, it's the ceramic membrane is an intriguing option, I would say, to help alleviate that.
Yes, we're very interested in the ceramics, so we're going to try to test that.
Okay. This is kind of a question I think any and all of you could probably jump in on. What can industry do to help advance the technology from your own, perspective? What do you think? And Andrew, why don't you lead off that one?
Yeah, I think in general, and I think we see this a lot more in Europe and maybe in some Asian countries, you see a lot more partnership between municipalities, industrial folks, the consultants, the manufacturers, all getting together and testing things and doing these kind of research centers at treatment plants, probably more so than you see in the US. And that's why you see a lot of great technologies come out, things coming out of Singapore or Germany, wherever it may be. And I think more of that would be helpful. I know that down in U of A, they've got some testing facilities. I know Dr. Rickman's doing stuff like that too. But I think the more we can partner and try to get these agreements together and not worry so much about risk and liability as we do in the States, I think that would help advance things faster. That's my own opinion.
Yeah, this is Bruce. I agree completely. And Andrew's right on target with this. And so my thing is just, I think we should, try to encourage pilot studies, because as Mike said, you really need to have them. And it's not a huge commitment. You're not building the full-scale plant, but, you can get people convinced of this. And so I think, we should be promoting more pilot studies.
Agree. And I think, the challenge, like on lab scale, is how well does a lab scale, scale up to full, and even sometimes there's challenges with pilot scaling up, but because we're in such an infancy still on this, at least start somewhere, right?
Yeah, it's really hard to do a bench scale test with one of these systems. So, the really important information is going to be gained from pilot scale.
Great, thanks, guys. Quite another question came through. Do you find any large changes in water qualities, such as pH, during these processes? I wonder if this could affect methane stripping. So I'm going to throw that out to any three of you, if you've had any know of knowledge or have experience on that topic. Going once, going twice. I guess, Mike, with the most field experience, do you monitor pH in the systems? Is that something that you
we're certainly monitoring pH in the system, and of course, as the pH changes, the amount of dissolved gases will change. So you would see a slight change, but like in that graph that Dr. Rickman showed, like most of the systems I'm working with, the majority of the biogas is coming out as gas. Like we have very little dissolved gas because the flows are so low. It's not like a municipal where, you have a large flow and in a low load. I'm on the opposite. Like the industrial projects are on the opposite end. They're low flow, high concentration.
Yeah. So let me just add to this. I mean, I don't think an anaerobic MBR is any different from any other anaerobic system. And the thing you have to watch is if you have big swings in loading of readily biodegradable material, like if you're putting in food waste and you get a lot more food waste or it changes its characteristics or something, and all of a sudden you get a huge load of really rapidly fermentable stuff, you can have pH problems on it. I mean, but that's not unique to membrane bioreactors. That's just, something you have to consider in any anaerobic system.
Yeah,
that's right.
The question for Dr. Rickman, the biofilm carriers that you mentioned, how are those mixed? How do you go about mixing those?
Yeah. Right. So they'd be mixed with a mechanical mixer. I think Andrew showed some pictures of which the kind of thing that you would do on that. So it would be some. Well, okay. So if you're using the biofilm carriers like the MBR carriers, then you'd have a mechanical mixer just to keep them moving. For the fluidized bed with granular activated carbon, that's just you have an upward flow velocity. You recycle the water and have an upward flow velocity on that. So it depends on what carrier you're using.
Okay. Another question came through, and we've got just probably a minute or so here. Does the physical environment impact the life of the membrane? For example, systems in Arizona versus Massachusetts. Mike,
I almost don't think it. I don't think it would that much, just because these they're in tanks, they're enclosed, they're kind of under similar conditions. It's more related to what the wastewater is treating would have more of an impact on membrane longevity, I think, than physical location. And maybe when it comes to municipal, that will be more important as temperature changes may have more of an impact on the membranes.
I'm not aware of any evidence of geographic issues for aerobic MBRs, and it would be the same kind of question.
Yeah.
Yeah, that makes sense. Okay, well, we're up on our time. I thank you all for donating your time and presenting to everyone here, and I thank everyone for taking their time out of their day for listening in. So, and Shayna, thank you for organizing this webinar. So everyone have a safe, fantastic rest of your day, and thank you very much.
Very good. Thanks, Nathan.
Thanks.